Pull up a flight tracker sometime and look at a long-haul route. New York to Tokyo, say. You'd expect the plane to draw something close to a straight line across the map. Instead, it arcs way up over Alaska, almost brushing the Arctic, before curving back down into Japan. For a long time, I assumed this was wind or airspace restrictions, or airlines being weirdly indecisive. It's none of those things. The plane is, in a very real sense, flying in the straightest possible line the entire way. The map is the one lying to you. So let's start with the simple case, the one your brain is quietly assuming by default. On a flat piece of paper, straight line has an obvious meaning. The shortest path between 2 points. The one a taut string would trace if you pinned it at both ends. Easy. That's Euclidean geometry, the stuff from 9th grade, and it works perfectly well for flat things. A sheet of paper, a football field, a whiteboard. Here's the complication. Earth is not a flat piece of paper. It's a sphere, or close enough to one that the difference barely matters for this part of the story. And once you're stuck living on the surface of a sphere, straight line stops meaning what you think it means, because you're not allowed to tunnel through the middle. You can only move along the curved surface. So the question becomes, what is the equivalent of a taut string, but for a ball instead of a table? Turns out, it's the same physical intuition. Take a globe, pin a piece of string at New York, pull it taut across the surface to Tokyo, and let it find its own path. It won't trace a smooth diagonal like you'd expect from a map. It'll bow way up toward the pole. That curve is called a great circle, the intersection of the sphere's surface with any plane that slices straight through the sphere's center. And a great circle is, on a sphere, exactly what a straight line is on a flat sheet. It's the path of shortest distance, and locally, at any tiny zoomed-in patch, it looks perfectly straight. Mathematicians call this general idea a geodesic, the straightest possible path on any curved surface, whatever shape that surface happens to be. If you're the kind of person who likes verifying things yourself, here's a fun one to try. Take a flat map, specifically a Mercator projection, the classic rectangular world map, and draw a straight ruler line between two far-apart cities. Then plot the actual shortest real-world path between those same two cities. They will not match. Not even close, once the distance gets large. The ruler line on the map is almost always longer in real distance than the curved-looking great circle route. This isn't a small rounding error either. Flying the straight-looking line from New York to Tokyo instead of the actual great circle route would cost you well over 1,000 extra miles. So why does the map lie to us this badly? Because you cannot flatten a sphere onto a plane without distorting something, either the shapes, or the areas, or the angles, or the distances. There is no projection that preserves all of them at once. It's mathematically impossible, which is a genuinely wild fact in its own right. The Mercator projection, the one basically every classroom map uses, was specifically designed to preserve angles, which makes it fantastic for old-school sailors who needed to hold a constant compass heading. But preserving angles means it has to sacrifice distance and area, badly, especially near the poles, which is also why Greenland looks the same size as Africa on that map when it's actually about 14 times smaller. Now here's where it gets genuinely strange, and where I want you to pause for a second if you want to guess the answer first. If great circles are the true shortest path, why do ships and some planes deliberately choose not to fly them? Okay, here's the answer. A great circle route requires you to constantly change your compass heading as you travel, because the direction toward Tokyo keeps rotating relative to true north as you curve up and over the pole. That's a nightmare to navigate by hand. So sailors invented an alternative called a rum line, or loxodrome, a path that holds one constant compass bearing the entire way. It's easier to steer, but it is never the shortest distance. It actually spirals slightly toward the pole rather than cutting the most efficient arc. So you end up with the exact same kind of trade-off you see everywhere else in navigation. The mathematically shortest path costs you constant course corrections, and the easy-to-fly path costs you extra distance. Efficiency versus simplicity, fighting it out again, just like burn schedules for orbital transfers. And it's not just planes and ships making this trade-off. The internet does it too. When you send a message across an ocean, it's very likely traveling through an undersea fiber optic cable. And the companies laying those cables spend enormous amounts of money and time plotting routes that hug great circles as closely as the ocean floor allows. Because every extra kilometer of glass fiber adds a measurable delay to your data. Light is fast, but it's not infinitely fast. And over transoceanic distances, the extra travel time from a badly routed cable is the difference between a video call that feels instant and one that has an annoying, noticeable lag. The shortest path problem that guided sailors 500 years ago is quietly still guiding the physical wiring of the modern internet. There's a neat structural echo of this in architecture too. Geodesic domes, the ball-shaped lattice structures you might recognize from Epcot's big silver sphere, are built by approximating a sphere's surface with a network of triangles whose edges all sit along, or close to, great circle arcs. The name isn't a coincidence. The whole design philosophy is about distributing structural load along the straightest paths available on a curved surface, which is part of why geodesic domes can enclose huge volumes of space using comparatively little material. And this "straight lines aren't straight" idea doesn't stop at the surface of the Earth. It goes all the way up to the biggest scale there is. In general relativity, gravity isn't a force pulling objects off a straight path. It's the absence of any force at all. Massive objects like the sun bend the actual fabric of space-time around them, and everything else, including light, just keeps traveling in the straightest possible line through that bent fabric. A planet orbiting the sun isn't being yanked into a curve. It's doing the space-time equivalent of a piece of string pulled taut, except the space itself is curved, so the straightest possible path happens to loop around and around. Light bending around massive stars, something we've actually measured directly, most famously during a solar eclipse in 1919, isn't light being pulled by gravity the way a ball gets pulled. It's light traveling in a perfectly straight geodesic line through space that has been warped into a shape where straight means curved from our outside point of view. And this isn't just a poetic way of describing gravity. It has direct, practical consequences for exactly the kind of navigation this whole video started with. The GPS satellites orbiting overhead sit deep enough in Earth's gravity well, compared to your phone on the ground, that space-time is curved slightly differently at their altitude than at the surface. Their onboard atomic clocks genuinely tick at a very slightly different rate than identical clocks down here, about 38 microseconds per day faster, once you combine the effects of their altitude and their orbital speed. That sounds like nothing, but GPS depends on comparing signal timing precisely enough to locate you within a few meters, and 38 microseconds of drift per day, left uncorrected, would snowball into a positioning error of several kilometers within about a single day. So every GPS satellite has its clock deliberately built to run slightly slow before launch, specifically so that once it's up in its actual curved space-time geodesic, general relativity corrects it back to matching Earth surface time. So here's the honest caveat, because I don't want to leave you with a picture that's cleaner than reality actually is. Earth isn't a perfect sphere. It's an oblate spheroid, very slightly squashed at the poles and bulging at the equator, by about 21 kilometers between the polar and equatorial radius. That sounds tiny compared to Earth's size, but it's more than enough to break the simple great circle math. On a true ellipsoid, finding the exact geodesic between 2 points doesn't have a clean, closed-form formula the way it does on a perfect sphere. GPS systems actually rely on an iterative approximation method, most commonly something called Vincenti's formulae, which basically guesses, checks, and refines the path over and over until it converges close enough to the true answer. There isn't a tidy one-line equation for it. I still find it a little funny that the reason a flight to Tokyo looks bent on a map is fundamentally the same category of fact as the reason starlight bends around the sun. Different scale, same underlying idea. The shortest path is whatever the space you're in decides to allow, and the space is very rarely as flat as it looks from where you're standing.